This is the end, beautiful friend. This is the end, my only friend. The end of our elaborate plans. The end of everything that stands. The end, no safety or surprise. The end, I'll never look into your eyes again. Can you picture what will be so limitless and free? Desperately in need of some stranger's hand in a desperate land.
Hello and welcome back. Of course, this is the end. This is the last lecture, last live stream for CSCE 310 this summer. Today you are going to be doing your final exam. Of course, it was released last night. It is take home. It is due at midnight tonight, like your last assignment. So the way the way that this live stream is going to go is, again, we're just going to do a review. I have the final from the two previous summers here, and we can go over as much as we want. Of course, I was not going to play the full Doors song. That would be like 12 minutes, and I'm not going to have that long of an intro. So, but of course, this is the end. This is the last day here. We hope to have everything graded, hopefully by over the weekend, by Monday. You should, hopefully you'll have your grades. Certainly, hopefully by the end of Monday, you should have your grades in. All right, so here's the final exam from a year ago, from last summer. And the first few questions are just graph algorithm questions. We give you a graph, directed weighted graph. Perform a depth first search on a graph in figure 1. Use lexicographic order to determine each vertex to visit next, starting at A. Indicate the discovery time and the order time and the finish time, indicate the discovery order and finish order of each vertex. Okay, so actually, what I'm going to do is let's go ahead and just take a picture of this, and I had it up before, but come on. Slow as hell because of OBS. Okay, well, while we're waiting for that to load, let's go ahead and just do the DFS here directly. We start at A. Hopefully, and this graph probably looks familiar. It's the same graph on your final. It's just that the edges, it's actually not the same graph. It's an isomorphic graph. We have switched around the vertex names and the weights so that it's not going to be the same answer. So don't fall into that trap. Oh, what are we doing here? I'm just going to write that down. It's not the same graph. So let's go ahead and do a DFS starting at A. All right. Well, here now that it's loaded. There we go, finally. All right, let's go ahead and bring over our graph here so that we can write on it. Okay, there we go. So I will go ahead and start out, let's see, at A. All right. Oops, let's do a highlighter instead. There we go. We'll start out at A here. A is now discovered. And we'll go ahead and write down the discovery times of each one of these things. So A, its discovery timestamp is 1, and then whatever its finishing timestamp will eventually get to that. What else do we have to keep track of? Determine which vertex to visit next using lexicographic order. Indicate the discovery order and finish order of each vertex. We don't have to draw a DFS tree here, a full DFS tree. We just have to do the write down the discovery time and the finishing time. Okay. So if I'm at A here, then where do I go next? I need to go. I could go to F. I could go to B, but lexicographic order tells me that I need to go to B first. Right? And B is discovered at timestamp 2. It's not yet finished though. And from B, I look at the neighborhood here, and we've got E, D, and C as unvisited vertices. C is, of course, going to be the next lexicographic next one. After that, we would end up, so C is going to end up being discovered at timestamp 3. After that, we only have 2 choices, D and H. D is lexicographically next, so D, and that gets discovered at timestamp 4. We still have options, so we're going deeper into the graph. D, its neighborhood, 2 things have been visited, but one thing is still a white vertex, unvisited vertex, so we'll go ahead and go to it next. G, that's discovered at timestamp 4, and we're still not done exploring deeply into the graph yet. So G at timestamp, 5. I think I said 4. So G has now a much larger unvisited neighborhood, so we've got a lot of choices here. E, F, or H. Lexicographically, E would be next. And so we go ahead and discover E at timestamp 6. And then, of course, we only have one choice left, and that's going to be F. And at that point, that's when we start backtracking. So E, F gets discovered at 7. F is done, so we end up, and I'll change my highlighter color here to red, done. Right. There we go. Or whatever combination that is. So that's been faded out. That's black. It is processed. It is done. And that was done at timestamp 8. And I'll increase the size there. Okay. We backtrack to E. There are no other choices. So we go ahead and timestamp that as a finishing timestamp of 9. We backtrack to G, and we do have an opportunity over here to go to F. So we go, H, right? And so we go over and discover H. We discover it, however, at timestamp 10. At that point, we start backtracking from H. H gets backtracked 11. Right? It gets finished at 11. And let's see, go back to my highlighter here. Pink. And that's done. Right? We backtrack to G, which is where we were. It gets done. And we timestamp it as 12 now. Right? We backtrack to D is where we came from, I believe, right? Yeah, because E is already done. Oops, I never colored E, sorry. But this is all we're looking for down here. Right. And, oh, you know what? Forgiveness. I never started the live Q&A on Piazza. So if you are yelling at me for any reason, apologies. Let me go ahead and start that really quick. All right. Anyway, we'll go ahead and continue here while that's loading up. D gets finished at 13, and it's just backtracking at this point. 14, C gets finished at 14, 15, and 16. Oops, 16. There we go. So there are all the finishing timestamps for the DFS run. Right. Okay. I'm going to go ahead and put on another copy of this so that we can do the next one, which is going to be BFS, but with a different criteria. I believe that these are the same criteria as in your assignment 3. where you had to implement this stuff, so it should be familiar. There, the live Q&A is started. If you have if you have any problems with this live stream, there we go. Sorry, should have done that before. Okay. So breadth first search, but use lexicographic order to determine which vertex to visit next. So it's not like your assignment where we use the weights to do it. So let's go ahead and establish that we're starting at A, right? So A gets discovered at 1, and it's not. I think we have we did say discovery and finish order here of each vertex. Again, it's not that big of a deal to see the finish order because it's going to be the exact same order as the discovery because it's FIFO, first in, first out. Okay, so we start at A, and I'll go ahead and switch my color over here to red. We discover A, we put it in the queue, we bring it out, and when we visit its entire neighborhood in lexicographic order, B and F. So those get discovered at 2 and 3 respectively. So B, 2, F3. Right. And then once we're done with that, A gets finished, processed, and so we can put that at it really depends if you put stuff into the queue first and then you process it, or if you process it and then put stuff into the queue first. It really doesn't matter because it's going to be the same ordering. Okay. All right, so then B comes out of the queue, and we're looking at its neighborhood, its unvisited neighborhood, and we put things in the following order: C, D, and E. Right? Remember that A has already been processed. Okay, so C, D, and E are next. And they are discovered at timestamps 5, 6, and 7. Okay. B gets finished, right? At timestamp, again, if we're processing after we've enqueued its neighborhood, then it'll be at timestamp 8, and the same ordering down here. In fact, this is acting as my queue. A is now gone, B is now gone, F is the next thing in the queue. And so I look at its neighborhood and see that, well, A has been processed, E has been visited, G is unvisited. So G is the next thing to get enqueued, and it's been discovered. It gets colored green in this case at timestamp 9. All right. Green, G, F gets processed, and it's processed at timestamp 10. Okay. The next thing to come out is C, and it's got a blackened vertex, a gray vertex, and a white vertex. And so we NQH at timestamp 11. We DQ, we then process C at timestamp 12, and update my colorings here. C has now been finished, right? And now the rest of the stuff is pretty straightforward because each one of these neighborhoods now, unvisited vertices are empty. So we go D, E, G, H, giving finishing timestamps of, where were we? 13, 14, and 15, and finally 16. Right? And that's all we needed to do for that exercise. If you want to, you can, show your work, but you could also, have, run it through your algorithm, like actually encode this graph in your assignment 3 encoding and see what it looks like, right? Do you come out with the same order? Check your work, basically. Right? Finally, I'm getting a lot of dropped frames recently, so just a second. All right, we'll try that again. I'm getting much better bandwidth now. I don't know what the issue was there, so apologies. Hopefully it's no longer dropping. All right. So there's a lot. This next one is just minimum spanning tree. You can use whichever algorithm you want. So we'll go ahead and use, I don't know, Kruskal's, where we will go in order of these of the edges, and we'll consider them in order of least weighted edge to highest weighted edge, right? And we'll only include them if they do not induce a cycle. So in this case, the first one is, of course, C to H. And of course, the first one, you're always going to take that. So we'll go ahead and, take this edge right here. Right? And I'll draw it nice and thick. There we go. The next one that we consider is going to be, there's one with two, there are a couple with two here. So if we want to go with lexicographic order to break ties, then it would be DG and then GF. And we're actually going to take both of those because taking them does not induce a cycle. So the order in which we take them, D, G, at a weight of 2, you take it. And I'm indicating that we've taken it by me graphically putting the green there. And then GF, we take that as well. The next ones that we consider are GH. And we take that because taking that does not induce a cycle yet. So GH at a weight of 3. Okay. And then what's left here? There's one with 4. And so we end up taking that because that does not induce a cycle, EF. And that's a weight of 4. The next one that we would take would be, let's see, I want to make sure I'm not missing any. So it looks like this one right here, EB, or BE, if you want to write it lexicographically. And that's a weight of 6. So BE 6. And again, it does not induce a cycle. The next ones look like these two 9s over here. Doesn't matter which one we consider first, but if we want to go again in lexicographic order, then it would be AB at a weight of 9. Now the next one we would consider is this one. The next one we would consider is this one, but we don't take that because that would induce a cycle right here. So we're not. I am going to write that down though. We did consider AF at a weight of 9 omitted. Right? Excuse me. All right. All manner of problems today. Likewise, DC, that would induce a cycle up here. Or CD, I guess. A weight of 10 omitted. All right. The next one that we would consider would be this BC. Of course, that would induce a very large cycle. Actually, sorry, I've lost a forest for the trees here. How many, literally forest for the trees? 1, 2, 3, 4, 5, 6, 7, 8. And we've taken 1, 2, 3, 4, 5, 6, 7 edges. We're done, right? So the algorithm at this point is terminated, right? Total weight is, I don't know, go ahead and add up all those numbers. 5, 12, 18, 27. Yep, and then we're done. Okay, great. Simulate Dijkstra's single source shortest path for the source being F. For each vertex, indicate the weight of the minimum weight path and its immediate predecessor vertex. Right? Oh, thank you. I gotta bless you online here, and I forgot that I had sneezed, so I was like, what? All right, so let's go ahead and do Dijkstra's, I guess. Come on. There we go. Increase the size here. Okay, well, that's too big. Because I'm going to keep track of all of these vertices down here. So down here are, this is going to be my Q. Right. And over here, this is going to be my final triples, right? So in my Q here, I'm going to set everything up with all the vertices starting at F. So F, its weight is going to be 0, and its predecessor vertex is nothing. Okay. Otherwise, I'm going to input everything else A as infinite and no predecessor vertex. Give myself some more room here. Don't need to double space it. B, C, D, E, F. And we already did F, G, and how many do we have? H, I think is the last one. So H, inf. Now, inf is the length of the shortest path from F. Okay, so with a single source, we're finding all the other the shortest path to all the other vertices. So we start out by looking at F's neighborhood, and we update everything in this queue here based on the distance that you can travel. So 2, I can get to G at a weight of 2. Well, before that was inf, right? So 2 is certainly better than inf. So I update all of those accordingly with a predecessor vertex. So I can get to G now at a weight of 2. How do I get there? I came there directly from F. Likewise, E, how do I get there? I can get there at a weight of 4, which is better than infinite, and I got there from F. And finally, A, oh, looks like I got rid of it. All right, A, inf, and nothing originally. And so we'll update that immediately here to 9, and its predecessor vertex is F. And by the way, when we did this, this jumps out of the queue and goes over here to our final triple. Okay. Now we look at this. This is a priority queue. This is a heap. We're going to pull the thing out that is the minimum distance, which is this G over here, right? Come on. And we'll put that into our final triple. It's been fixed, right? So one way that you can look at that is that you have fixed this path right here, right? And I'll visualize that as we go along, okay? But we now need to look at G's neighborhood. I can get to G at a cost of 2 or a weight of 2, and then I can go on to H at a cost of an additional 3, right? So is 2 plus 3, is that better than what I found before with H? Well, H was infinite, so anything is going to be better than infinite, so 5. And its predecessor, remember, I'm working from G now, so its predecessor is going to be G. D, I can get there at a weight of 2 plus 2, which is certainly better than infinite, so 4, and a predecessor of G. I can get to C from G at a cost of 2 plus 13, 15. That is not better than what I've found so far, 4. So I end up not updating that. The next iteration, I have a tie to break here. I could pull out D or I could pull out E. They're both weighted as 4. I'll go ahead and go in lexicographic order. There we go. And now that has been fixed. I came from G, so I'm going to go ahead and highlight that edge right there. Okay. And now I look at G's neighborhood. Of course, I don't look back. I only look at B and C, which were not reachable before, but now they are. To get to D costs me 4. To go on to B would cost me 12. So that's going to be 16 and a predecessor vertex of D. I can get there 4 plus 12, 14 for predecessor vertex of D to C. Next iteration, I take out that one that I was breaking a tie with. And I fix that E. Where did I come from? I came from F, so that corresponds to this edge right here. Now I look at E's neighborhood again. This is already in my Dijkstra's tree. This is already in my Dijkstra's tree. The only thing that that's not in my Dijkstra's tree in the neighborhood is B here. And so I see that I can get to E at a distance of 4, right? And I can go on to B with a weight of 6. So 4 plus 6, 10. Is that better than what I've found so far? Absolutely. Update that. and change the predecessor vertex to E. Next iteration, take out the H, because it's the least weighted. And that corresponds to H. I came from G, so there's H, and so that corresponds to that edge right there. Of course, you can rebuild that afterwards. I'm highlighting it as we go along. And we look at its neighborhood. I can go to C at a weight of 1. I got to H at a weight of 5. So total 6, I can get to C, which is better than going through D. And I'll update the predecessor vertex there. And that ends up being what I pull out of the priority queue next. And that fixes this edge right here. Then I look at its neighborhood, and I can get to B at a cost of 11. Well, I got to C at a cost of 6. So 6 plus 11, 17. Is that better than going through E? No. So I end up not changing anything. I pull out this next one, A, 9. And that is just directly from F there, right? I can go to B at a cost of 9 plus 9, which is not better than 10. So I end up not updating that. And of course, on the last iteration here, you just pull this out, and there's no neighborhood left, unvisited, undiscovered neighborhood to find here. So I end up going to B from E, and there's my Dijkstra tree. Okay. All right. All of that was basically plug and chug, as in if you knew the algorithm and you could simulate it really quickly, or throw it into and then throw it into your program to verify it. Great. This is a repeat. I reuse this. This is a repeat from our review from quiz 4. So if you want to see the full thing here, you're just searching for probabilities. What is the expected number of key comparisons made in this tree? We did that already. So I'll skip that. This is clearly not optimal. Draw an alternate BST with these keys with a better expected number of key comparisons and compute the number of key comparisons. Your tree does not have to be optimal, just a better one than in the figure. So there's a clear hint here that you should put baseball at the top, as you should do in life anyway. Right. Baseball. If I put that at the top, then 0.40 of the time I will only have to do one comparison. Right? Now, you got to be careful here. This is still a binary search tree. So by putting baseball at the top, they are listed in order here. Baseball, football, hockey, shinty, shirling. All right, that's an alphabetical order. So I can't just go and put anything. I can't put football over here as its left child, because that would not conform to the order. I have to put something over here. And so I'll go ahead and choose, oh, football is the most common, so let's go ahead and put it over there, football. Right? And that takes 2 comparisons to get to at a probability of 35%. Right? If I chose to do that, then hockey, shinty, and shirling, those are all, again, A, B, C, E, F, G, H. Yep, I have to do that every single time. It'll never not be that way. I could put hockey over here. Right. And shinty and shirling, I would have to necessarily then end up putting them like shinty and then shirling. Right. And so these are ever increasing here. Hockey would end up being 13% of the time you do 3 comparisons. Shinty, you would end up doing 4 comparisons or 5 comparisons for shirling, with 0.04% probability, 0.08% probability, and you'd have to add all these up to see if it's actually better. If not, then of course you could rebalance this a little bit if you want to. You could put shinty at the top, and then hockey down here, and shirling over here. It would lead to a slightly shallower tree, maybe a better probability, but I'll leave you to add that up on your own. Right? It's not an arithmetic course. Provide an example distribution on 3 keys, A, B, and C, such that choosing the highest probability key as the root leads to a suboptimal binary search tree. I think that if you just take the one from the notes, where you give such that choosing the highest probability key as the root leads to a suboptimal, all you have to do is make sure that your other two keys are forced to be down here, and then maybe like say, I don't know, 50% is up here, but this ends up being 40% and 10%. So you're paying more down here because now you have 1, 2, 3 key comparisons 40% of the time versus this is A, B, and C, right? Versus if you'd been a little bit more balanced, then yeah, you'd have to pay more on that end, less on this end. It's definitely, but the point it being is it's not optimal. Sorry, there we go. But just taking the one from the notes, I think that's enough. That's why I asked that question. Did you read the notes? All right. Okay. Suppose that we need to generate all combinations of vertices in a graph with n vertices for a brute force algorithm we're developing. To do so, what order would the algorithm be? Order, as in like big O, right? So all combinations of vertices of a graph with n vertices. So, I mean, in general, if you want to select a subset of size k, then there's n to the k. But this one is asking for all possible combinations. In other words, sum them all up for a subset of size 0, a subset of size 1, a subset of size 2, ... all the way up to a subset of size n. N choose 0 plus n choose 1 plus n choose 2 plus ... n choose n. And you can look that up if you really want to, or you can just say, well, that's the power set. That's going to be 2 to the n. And so it's going to be order 2 to the n. Suppose we need to generate all possible orderings of edges from a graph with m edges for a brute force algorithm we're developing. To do so, what order will the algorithm be? So if there are m edges, all you have to do is, well, it's going to be order 2 to the m instead. Right? It's just a variable change. Not hard. I don't like asking, difficult questions on an exam. Under normal circumstances, you'd be taking this in class. And thinking questions are way better than plug and chug questions, but I do put on plug and chug questions like the algorithms above, just so that if you know the algorithms, you're at least guaranteed 50% of the points or something. Suppose we need C. All right. So like in your homework, what I suggest is that you start drawing pictures with these things. You start drawing the complexity landscape here of what we think it looks like. P and NP complete. All right. Now I'm going to use a pencil here because we're going to now set up what this problem is asking us. I'm going to picture it here. So suppose P1 and P2 are problems in NP, so they're somewhere in here, and that P2 is NP complete. So in other words, we can put it right here, P2. All right, so it shows up. I'll go ahead and do it in pen. Okay. Further, suppose that P1 reduces to P2. So it could be that P1 is down here and it reduces to P2. It could be that P1 is down here in the intermediate and reduces to P2. It could be over here as an NP complete as well, and it still reduces to P2. Why? We know that P2 is NP complete. By definition, we know that everything in this complexity class reduces to it. Right? That's just the definition of NP completeness. So can you conclude that P1 is NP complete or not? In other words, can you say that P1 is in here? And no, you can't. Because by the definition, it could be over here, or it could be over here. And that's the justification you give. No, it could be that P1 is in P, and it still reduces to P2 because that's the definition of NP complete. Right? Again, suppose P1 and P2, this is D now, are in NP, and that P2 is NP complete. So I didn't, I wrote it in pen and it's still fine. Further suppose that P2 reduces to P1, right? So if I reduce P2, reduce goes upwards to P1, then we have this kind of picture, right? But remember, P1 and P2 are both in NP. Therefore, necessarily, P1 has to be NP complete. because transitivity-wise, everything reduces to P2, to P1. Therefore, by transitivity, everything reduces to P1. Now, can we conclude that P is equal to NP? No, we can't. This is just a normal situation, right? If I had said that P1 is down here in P, and so it said, well, P2 reduces to P1, that would certainly collapse everything, right? But the reductions always go upward, at least visually. Okay? So when you're doing your homework like that, my suggestion is to draw a picture in order to think it out. We have some extra time here. So here's the midterm from 2 summers ago. I don't like redrawing graphs, so I just reorder the vertices and change around the weights, right? Depth first search. I'm not going to do these again since we did them all for one example already. Dijkstra's, et cetera, et cetera. But no, I'm not doing that one. Sorry, I'm not doing your actual final exam for you. Right? I think that was on the final. I'm not sure, right? But it's not in the same form. Suppose that T is an optimal binary search tree with n keys. What is the maximum depth of T? This is just a red herring. Optimal binary search trees do not have to be balanced, so it could be completely unbalanced all the way to the right, right? And if n is 4 in this example, what's the depth? 1, 2, 3. So in general, if you've got n keys, ... in the center, then the depth is n minus 1. Okay. Suppose that we have 7 keys and want to create an optimal binary search tree, but the probabilities are uniform. That is, each key has probability 1/7. What would the tree look like? I don't have to tell you anything more other than the probability distribution is uniform. Right? The best tree is going to be a balanced tree, because there's no reason to make it deeper because everything has the same equal weight. Right? You're back at square one. Consider the following root table generated by the optimal binary search tree algorithm. Draw the corresponding tree. The keys, of course, are 21, 33, ... Right? So this one I might have trouble on, but that's okay. So they're 1 through 8. What is the root? I just simply need to look at row 1, column 8. Oh, it's 52. Right? And so I start with 52 as my root. Right? They're ordered. It has to be a binary search tree. So that means that there are 4 keys on the left and there are 3 keys on the right. So let's go ahead and build the left tree first. Right? 1 through 4. The root there is going to be 21. Right? Because of the table here. 1 through 4. That means that the left subtree there now is empty, and I'm only dealing with 33, 35, and 38. Or keys 2 through 2 through 4. So 2 through 4 tells me that 35 is the root of that subtree. And now I don't have to look up anything more, because 33 and 38, if there's only a single node there, then that's all you can do. Let's take care of the right subtree here, which again was 72 through 93. Or if you're looking at the indices, this is 1, 2, 3, 4, 5, 6, 7, 8. So 6 through 8. Right? That's going to be 6, 8, 93. Right? And that means that the right subtree is now empty. The left subtree has both keys 72 and 76, which correspond to 6 through 7. Right? So 6 through 7 is 76. Right? And then now no more work. It's just 72 is the left child. Okay? And there is the optimal binary search tree for those keys given this tableau right here. Okay. More NP complete scenarios. So let's redraw our landscape here. P, NP complete, and NP out here. Right. So Say that P1, P2, and P3 are problems. That's the only thing, right, that we're given. As now A, say that P1 reduces to P2 and that P2 is NP complete. So here's P2, right, and it's NP complete, and P1 reduces to it. Can we conclude that P1 is NP complete? Why or why not? That's the exact same as before. No, it could be anywhere. It could be P1 could be down here in P, and of course it would reduce to an NP complete problem. Say that P1 is reduces to P2, and that P1 is NP complete. So P1 is NP complete, right? And that P2 is in NP. Well, of course. Can we conclude that P2 is NP complete? Yes. So P1 reduces to P2. If we said we started out with the fact that P1 is NP complete, then everything reduces to P1. P1 reduces to P2. Therefore, by transitivity, P2 has to be in this NP complete area. Right? That's why I like drawing it like this, because if you think about reductions as going upward, then well, there's no place for it to go if it's in NP. It could be, of course, up here, and then we reduce outside of the set, but that goes beyond what we've covered for this course. You like that kind of stuff, take a complexity theory course. Say that a P1 is down here in P, and that P2 is NP complete. So restore that. Let's see. Can we conclude that P1 reduces to P2? Absolutely. That's by definition of being NP complete. P1 is in NP is in P. We know that P. This is the only thing that we know, is that P is a subset of NP, and therefore P1 is in NP and it reduces to P2, which is NP complete. That's by definition of P2. Right? P2 being NP complete. All right. Say that P1 is NP complete. And that P2 is in P. So it looks like this might just be the opposite. And that P1 reduces to P2. That doesn't look right to me. Can we conclude that P is equal to NP? Yes. Right? That's what collapses everything. If reductions suddenly go downward from NP complete into P, that means that P is equal to NP. Right? That is not, of course, a proof. It's why? Well, this is NP complete. If we can reduce it to P2, and we know that it's in P, then that means that we have an algorithm for P2, which means that we have an algorithm for P1. Simply just reduce instances of P1 to P2, use your algorithm that supposedly exists over here to solve it, and you've solved the original problem over here, right? For decision problems, right? In fact, that holds for any NP complete problem, not just this particular one, right? But universal generalization, I didn't say what this problem was, and so, yeah, of course, P is equal to NP. Okay, that's the end of that midterm. All right. I don't see any questions on Piazza. So hopefully everybody has gotten a good start on it. If you're a night owl and we're working on it last night, great. If you're already done, great. Otherwise, thank you for taking this course. This is the first time that we did 310 online. We did it because we had to, but we were already going to do something like this anyway in the program. You'll probably see many more online or hybrid or dual offerings. For example, Computer Science 1 this fall is going to be have two sections, an online section and an in-person section, and it will continue to do so. That's just the future. This is the future right here of higher education, likely. Let me know how it went, especially with the course evaluations. I believe that they did the course evaluations. If they didn't, weird. If they didn't do course evaluations, I still want to hear from you. Often, we didn't have too many technical difficulties. I have decent internet here. I don't know if that was the issue. I've noticed lag sometimes, especially here. But I don't know if it actually impacted the live stream. If you watched it later, what did you find helpful? What did you find useful? Please let me know about all those things. Because likely I'm going to be doing something like this with CS1 and for all the courses from now on. I've actually been broadcasting all of my courses for the last couple of years. It's just I've been using a different tool called VidGrid, and sometimes I've used OBS to live stream. But I'm always interested in hearing more. If in fact it was laggy, then that just justifies that we need better equipment here. And then I get to spend some money and get some new toys. So let me know if how it was, how it went. Let me know how it can be improved. Look, from the stats that we've been collecting, it looks like a pretty typical semester for a summer offering, at least, of this course. So congratulations on completing this course by midnight tonight. I wish you well in your fall courses, or if you've got an internship this year. Thank you for taking this course, and have a good rest of your summer. Which, unfortunately, if you are taking courses, is only one more day and a weekend.